has this capability. Although tensile steel found its initial use in bridge design, it is now being used in a wide variety of architectural applications. If we can understand and differentiate to identify the members that are only ever subjected to tension and those that experience compression, we can use this knowledge to create force-differentiated structures. The design of the steel system on the Grand Arch made clear use of more substantial members to resist compressive forces and thinner cables to resist tensile forces. The design for Porto International Airport continues in this established tradition of force differentiation to create a highly energetic arch system that spans across the departure hall. So in the instance of the design for the Porto Airport, this has allowed for the use of much thinner rods to stabilize the structure. It is pretty clear here that the curved bottom chord of the truss is a compressive member by its size, and that the horizontal ties are in tension. The tubular web members of the truss are acting in compression, but can be smaller due to the decreased compressive loading. The most normal way to connect tension rods to plates is through the use of a clevis. These make simple rotating pin connections. The bottom chord of the innovative trusses in the Pudong Airport use rods, as these elements are always acting in tension. The attachment between the rod and the hollow structural steel compression member is achieved with this innovative steel ball connection. If multiple tension elements are connected via clevises, the geometry must be planned carefully to ensure that the plate to which they are attaching has enough steel and adequate distance between the holes that are drilled to accept the pin connections. As can be seen in the design of this bridge, the fan-like geometry of the tension members has resulted in a varied spacing of the supports to the bridge deck. Had their spacing been required to be even, this would have changed the design of the plate at the top of the mast. Inside the curved glass dome of the Reichstag, a spiral ramp fabricated from custom sections of plate steel is hung from the ribs that form the dome. The spiral walkway inside the Reichstag dome uses a tension suspension system. The ends of the rods use clevis attachments. A custom clevis has been designed to neatly accept two incoming rods to simplify this connection. A tension system is used here to assist in making the span, absorbing some of the gravity forces from the bridge-like connection between these buildings. The plates that connect the tension members to the primary structure are custom formed to accommodate two rods. A turnbuckle is evident. These are used to align and tighten the system as it is being erected. The connector at the lower extreme of the tension member keeps a similar aesthetic, but only needs to resolve a single member in this case. This pedestrian highway overpass uses a tension system to suspend the walkway from steel arches. This is a view to the underside of the bridge, showing the unusual support system for the walkway that has been created with inverted T-shaped steel sections that have been welded to a central round HSS spine. The ends of the inverted